Thanks a lot, Ramesh.
Thank you, sir.
Let's give it another 1 minute. Do any of you have another class just before this from 12 to 1:30? Okay, I guess we can start. So let's just do a quick recap of what we looked at last time. First, we saw various kinds of numbers, natural numbers, integers, real numbers. Then we looked at coordinate systems. So for example, X, Y, Z. And then we went on to looking at graphs of various functions. And we looked at examples for a number of them. And we asked the question, when is a function equal to 0? Or what we call finding the roots of a function. And then after that, we looked at complex numbers. We just started looking at complex numbers. We'll continue that discussion today. So do any of you have any questions regarding what we did last time? Or do you want me to repeat some part that is not clear? How do you feel about the pace? Do you think this is going too slowly or too fast? Is there anyone who thinks this is going too fast? You can raise your hand in the chat. Okay, is there anyone who thinks this is going too slow? Okay, can you all hear me? I'm a little worried that I'm just speaking to myself and nobody's being able to hear.
We can hear you.
Okay, perfect. So I'm guessing the pace is okay for most of you. Fine. So then we'll continue at a similar pace. So we'll continue with our discussion on complex numbers. Just to remind you, we started off with saying that a complex number is of the form a plus ib, where I is defined as square root of -1. This is an imaginary number. A and B are real numbers, and we refer to them as the real part of the Z and the imaginary part of Z. Now, what you can do is you can add and subtract and multiply and divide them. You can also define what is called the complex conjugate of Z, which is given by, it's denoted by Z star. And you just make the sign of the imaginary part negative. And if you do z multiplied by z star, you have a plus ib, a minus ib, which is a square minus I square b square, or a square plus b square, because I square is -1. So this also gives us a way of defining what is called the magnitude or the absolute value of z. So this is square root of a square plus b square, or you can write it as square root of zz star. What does this mean? We can draw a graph and represent complex numbers graphically, where on the x-axis we put the real part of z, and on the y-axis we put the imaginary part of z. So any number a plus ib is going to be marked as a over here, b over here. So this is your a plus ib. And then what this a square plus b square means is just the distance of this point from the origin. So this is square root a square plus b square. Now this gives us one more way of representing complex numbers in terms of the distance from the origin and the angle that it makes with the x-axis or with the real axis. So if I define a square plus b square, if I denote it by r, and if I denote this angle theta by b over a, then you can see that a is just r cosine theta and b is just r sine theta. So z, you can write it as r cosine theta plus I r sine theta. And r cosine theta plus r sine I r sine theta can also be written as r e to the power I theta. So these are all equivalent ways of writing the same complex number. If you write it as in terms of a and b as a plus ib, that's one way of doing it. But you can also write it in terms of r and theta in this trigonometric fashion or in this exponential fashion. These are all the same complex number. Any questions so far? Okay.
Professor?
Yeah.
Yeah, so I haven't done complex numbers, so I just have like a basic simple doubt. So if it's the conjugate of the same complex number, so how is that represented on the graph?
Right. So let's take some complex number. Let's say this is a plus ib. Or if you want, I will use some other letters because a plus ib. Let's call this p plus iq. What this means is that this distance is p and this distance is q, right? Now, the complex conjugate has the same real part, but the imaginary part has a negative sign. So that means for the complex conjugate, you still have the same p, but now q is negative. So this is minus q. So then p minus iq is over here. So when you take a complex conjugate, it just flips the complex number about the x-axis. So what is up comes down, what is down comes up. Does that answer your question?
Yeah.
Any other questions? Okay. What else do I want to cover in complex numbers? Well, nothing much really. Okay. So Well, towards the end, last time somebody asked a question as to whether, like we have functions of real numbers, whether we can also have functions of complex numbers. Yes. So you can define a function f of, just as we have some function f of x, which is x square or sine x, etc. You can also define functions of complex numbers, z square, sine z, etc. Because complex numbers are more complicated, there are certain complications, certain weird points that arise when we take functions of complex numbers. And if you want to read up more about complex numbers, great, but I don't think we'll discuss any of those in class right now. Some of you may have already looked at those in advanced maths courses if you've taken any. Okay. Now we've been talking about functions all this while, but we've never really defined what a function means. So does anyone have any idea what is the meaning of function? What does it mean actually? Any guesses? What do you think when you see the word function in the mathematical sense?
It's something that takes an input of set A and um, transforms it into a set B given by whatever the function does.
Right, that's one way of looking at it. So what you're saying is, suppose I'm saying f of x is x square. It's like a machine called f. It takes a value x and then it spits out a value x square. So yeah. So mathematically, what a function is what we call a map. From, as you pointed out, from one set to another. And it has certain kinds of maps are called functions. So let me show you what a map is. So suppose I have one set A and I have another set B. And these sets have certain elements in them. These are not potatoes. And what a map is just something that takes elements of A and converts them into elements of B. So for example, you might define a map which takes this element to this one, this element to this one, this element to this one. This one might also go to the same one, and so on and so forth. Or this one might go to two of them, and so on. So there are four kinds of maps that you can define. You can have a one-to-one map, a one-to-many map, a many-to-one map, or a many-to-many map. Are the names kind of, do the names intuitively make sense? One-to-one means that every element in A is going to be mapped uniquely to some element in B. You will never have one element being mapped to two different elements, or you will never have two different elements being mapped to the same element. This will not happen. Then that is a one-to-one map. One-to-many map means that the same element in A may be mapped to multiple elements in B. That's one-to-many. Many-to-one means that you can have many of them in A, all of them going to the same element in B. And then, of course, many-to-many is all kinds of things happening. So these are all maps, but not all of them are functions. The only ones that are functions are the one-to-one map and the many-to-one map. So these two are functions. And these two are not functions. Any questions about this? Okay.
Professor Rutuja has a question in the chat.
Sure. Oh. Function is like a relation. Okay. Relation actually means something else in mathematics. But if you're using it colloquially, then yes, it relates elements of A with elements of B, if that is what you mean. Now, you can also define, you can also make two other classes of functions. You can have into functions and you can have onto functions. Let me just give you some pictorial examples of them. An into function looks like this. Suppose you have a set A and you have a set B. You have some elements over here and you have some elements over here. And now I'm going to draw a function which, let's say, takes this one here, this one also here, this one here, this one here. So this is clearly a many to one function because you have the first two elements of A going to the same element in B. So this is many to one. But you will see that there are some elements of B that are left over. They did not come from any element in A. So if this is a function in which the set B has some leftovers, then this is called an into function. On the other hand, suppose I have sets A and B. Again, this is a many to one function because second and third element of A are mapped to the same element in B. But now you will see that B has no leftovers. We are not talking about leftovers in A. If you're defining a function starting from A, then for every element in A, you have to define where it goes to in B. So A will never have any leftovers. Question is whether B has leftovers. So if B has leftovers, then it's an into function. If B has no leftovers, it's called an onto function. So Kostov says, what's an example of an into function where we have more images in B than we have elements in A? Sure. So let's take some, any questions so far about what into and onto means? Then I'll go to examples. Okay. So suppose how do you test a function for into-ness or onto-ness? So suppose I define the function. I have to define what the set is because I need what the set A and B are. So I'll define a function from the set of real numbers to the set of real numbers. Usually most of the functions that we deal with, they are from real numbers to real numbers. Defined by f of x is x square. So we have seen last time what the graph of this function looks like. It looks like a parabola. Now, you will notice that 1 gets mapped to 1, 2 gets mapped to 4, 3 gets mapped to 9, and so on. But also -1 gets mapped to 1, -2 gets mapped to 4, -3 gets mapped to 9, and so on. But the negative axis never comes from anything. So there is no real number x for which x square is negative. So this is an onto function. In fact, this is a many to one onto function. Why is it many to one? Because -1 and 1 are both getting mapped to the same number. -2 and 2 are both getting mapped to the same number. So it's many to one. And it is onto because these negative values were never used. Now you can say, okay, suppose I define it as f not going from the entire real numbers, but only from the non-negative real numbers. So let's call it r plus, meaning, not here, r going to r plus and including 0. So these are all the positive real numbers and 0 as well. Then my graph basically stops over here. It doesn't go down. And it looks like this. Now this function is a many to one. Sorry. This is into, this is onto. So you can, Summer says you can construct any set A and B and any fx to satisfy what you need. Yes, and whether B is exhausted, that tells you whether it is onto or into. Kaustav says, how do you figure out analytically and not through brute force enumeration? No, you would have to enumerate it. Because as you are seeing, it depends on what set it is. So you will have to check if there is any element in the set which is not being used. Well, one can also, okay, I wasn't planning to discuss this, but fine. If a function is, yeah, but graphically is basically enumeration, right? I assume. Okay, there is a theorem which says that a function which is one to one and onto, and there's a special name for it. This is called a bijective function, is invertible, which means you can find the inverse of this function. So like, for example, in this, when I said f going from real numbers to real numbers defined by f of x is x square, this is not an invertible function, because if I ask you what is square root of -3 or -4, then this has no answer. And also if I ask you what is square root of 4, this does not have a unique answer, because it can be 2 and -2. Okay. Any questions? Let's look at some examples. What can you say about this function? F from real numbers to real numbers defined by f of x is equal to x. And if you want, I'll plot the graph for you just to help you. This is just straight line through the origin. Is this 1, 1 or many 1? And is this into or onto? So to check if it is 1 to 1 or many to 1, you just check, is there any point which is any point on the y-axis which is mapped to multiple points on the x-axis? Well, turns out there isn't in this case. So this is 1 to 1. And also all the points on the y-axis are used up. So this is onto. What if I take the function f from r to r? F of x is equal to k, some constant. So the constant function looks like this. So is this 1-to-1 or many-to-one? This is again, no, this is many-to-one, because no matter what value of x you take, the answer is always k. So this is many-to-one. And is this into or onto? Yes, this is into, because none of the values except for k are used up. Only k is used on the y-axis. If you ask which real number gets mapped to some other point over here, well, the answer is there isn't any. So this is an into function. There are all of these points. These are all leftovers.
Professor, could you please repeat why it is many to one and not? I don't understand why it is not one to many.
This one, f of x equals k.
Yeah.
Okay. So f of x equals k means no matter what the value of k is, the value of the function is k. No matter what x is, it's always k. So f of 1 is k, f of 2 is k, f of 39 is k, f of minus 5.2 is k. So all of these points are all being mapped to k. So many to 1. Does that make sense?
Yes.
What if I took this? Instead of making my line horizontal, what if I made it vertical like this? Then what do you say? Yeah, this is actually one to many. So it is not a function. This is a one to many map, but not a function. Because over here, what happens? So suppose this number over here is k. Basically, you're saying f of k is 1, but f of k is also 2, f of k is also 3, f of k is also 4. So this is 1 to many. And that is not a function. Only many to 1 and 1 to 1 are functions. Okay. Let's look at some further examples. What do you think of sine x? Yeah, so sine of x is many to 1, because you know that sine of 0 is 0, but sine of pi is also 0, and sine of 2 pi is also 0, and so on. So this is many to 1. And is it into or onto? Well, let's say this is f from R to R. Then I will say this is into, because sine always takes values between -1 and +1. So all of these values, 2, 3, etc., -2, -3, all of these are unused. There are no real numbers for which sine of that number is going to give you 2. So this is an into function. But I can make it onto just by redefining my B set over here. So if I say f goes from R to the range -1, 1, and then I say sine x, then this is many to 1 and onto. Okay. Any questions on this? Great. So we've done straight line. Have you ever looked at the equation of a circle? So if I, on the coordinate axis, if I want to define a circle which is centered at the origin and has a radius r, then the equation of this circle is given by x square plus y square equals r square. Have you seen this before? Okay. Or in other words, I can also write x square by r square plus y square over r square equals 1. And then what I can do is I can generalize this. Suppose these two r's are actually not the same if they are different. So if I say x square by r square plus y square by s square equals 1, then this actually becomes an ellipse. Where this is r and this is s. So that's the relation between a circle and an ellipse. What if I want to have my circle not centered at the origin, but centered at some point, some other point? So let's say this is my origin. Suppose I have some point A comma B over here, and I want to have a circle with the center over here with radius r. Then I just have to move my x and y by these values A and B. So instead of this formula, it will become x minus A and y minus B equals r squared. Similarly for the ellipse as well. Okay. What more did I want to discuss? But we keep asking questions, yeah? So the next topic that we are going to discuss is scalars and vectors. What is a scalar and what is a vector? So there is a detailed mathematical definition which has to do with transformations, but we won't go there. For our specific purposes, a scalar is just something which is just a number, and a vector is something which has not just a number or not just a magnitude, but it also has a direction in space associated with it. What one can do is, let's talk about two-dimensional vectors for the time being. So this is the x and the y axis. Suppose I have 2 points, let's say a1, b1 and a2, b2, and I want to define a vector v from a1, b1 to a2, b2, then that is given as a2 minus a1 I hat plus b2 minus b1 j hat, where this I hat and j hat, they are called unit vectors. So this is the unit vector along x-axis, and j is the unit vector along y-axis. So all it says is, I had just says take one step of size 1 along the x-axis. J had just says take one step towards the y-axis. That's what J says. So that's I and J. And this is how you represent the vector. Once again, this is actually very similar to what we did for complex numbers. So you can again add and subtract vectors. So if I have one vector which is phi I plus 2j, and then I have some other vector which is 3i minus j, then you can always add them component wise. So this is 5 plus 3 in the I direction and 2 minus 1 in the j direction. So similarly, you can also subtract vectors from each other. Scalar, of course, is just a number. Can you give me an example of a constant scalar?
Pi.
Okay, 9, sure.
No, I said pi, but okay, 9 also.
Did you say 5?
Pi. Pi.
5. Okay, these are all constant scalars. Very good. You have given 3 correct answers. Or I have heard 3 correct answers. You gave 1 correct answer. I heard 3 correct answers. That's a one to many map. How about a constant vector?
I cap or any unit vector.
Sure. This or something like this. What's a scalar variable? How about something like x? So it's a scalar in the sense it's just a number, but it depends on what the coordinate is, what location you are at, or x, y, or x plus x, y sine x. These are all variable scalars. And what would be a variable vector? Something like xi plus xyj. So the x component and the y component don't necessarily have to depend only on x and y respectively. The components can depend on all of them, x, y, z, everything. It's just that this is the component in the x direction and this is the component in the y direction, right? Okay. For the vectors, similarly to what we did for complex numbers, you can define what is called the magnitude or the absolute value or the length of a vector. So if you have some vector v, which is given by ai, bj, and of course if you have the z direction as well, then there is also the k unit vector along the z axis. And then the magnitude, which is denoted in this fashion, is defined as square root of a square plus b square plus c square. Any questions so far? Can you give me some examples of vectors in real life? Yes, vectors show direction and magnitude. So this is the magnitude that we have just written over here. and the direction is basically given by the components in each direction. So let's again go to the two-dimensional case. If you tell me that there is a vector which is given by 2i plus j, then I know that I need to go 2 steps in the x direction and 1 step in the y direction. And then this is my vector. So it has a certain length, but it also has a certain direction. From the origin, this is at a specific angle. Now there is something very useful known as the triangle law of vector addition. So this law says that suppose I have a vector v, and from here let's say I have a vector w, then the vector x, which goes, so vector v goes from a to b, vector w goes from b to c, then the vector x, which goes from a to c, is going to be the sum of these two because they form a triangle. Or if you prefer, AC is AB plus BC. So this is called the triangle law. Kostav is asking, how do you find the angle of a vector with respect to the axis? The same way as we would with a complex number? Yes. Thanks, Samar. So it's exactly the same way with trigonometry. So let's say you had a vector like this. So you know that this is the xi part and this is the y. We shouldn't call it xi. Let's say it is ai and bj. Then from trigonometry, you can see that tangent of theta is going to be b divided by a. So trigonometry helps you find the direction. Of course, now if you're in 3 dimensions, it becomes a little more complicated. Then you have to use something called direction cosines. But the basic idea is the same. You will use trigonometry to find out what the angles are. So this was the triangle law of vector addition. Let's now talk about, let's do this. Okay, multiplication. This is interesting. There are 2 ways of multiplying vectors. You can define what is called the scalar product or the dot product, and you can define what is called the vector product or the cross product. In the scalar product, your final answer will be a scalar. So you will multiply 2 vectors and get a scalar in the end. And there are 2 ways of defining it. You can say, and it's written as, so if I say I have V, which is V1I plus V2J plus V3K, and I have W, which is W1I plus W2J plus W3K, and I want to find the scalar product of these two, then I write V dot W is V1W1 plus V2W2 plus V3W3. Or I can write it as magnitude of V times magnitude of W times cosine of the angle between V and W. So if I have a vector v like this and a vector w like this, then the cross product is given in terms of the magnitude of v, the magnitude of w, and the angle between them. Any questions? So using, let's say, using this formula, wait, I'll write it again. Can you tell me what will be the dot product between the unit vectors I and j? So remember that these are unit vectors, which means that their magnitude is 1. And because one is along the x-axis and one is along the y-axis, the angle between them is 0. Angle between them is 90 degrees. So this is 1 times cosine of 90 degrees, which is 0. How about I dot itself? So this is, again, magnitude is 1, and the angle between any vector and itself is 0. So this is 1. In general, whenever two vectors are perpendicular to each other, so the angle between them is 90 degrees. Cosine will always be 0. So in general, if the dot product of any two vectors is 0, it necessarily means that the vectors are orthogonal. Unless, of course, one of their magnitudes is 0, but having a vector of 0 magnitude is not really interesting. So as long as you have two non-zero vectors whose dot product is 0, it means that these two vectors are orthogonal or perpendicular to each other. Good. So if I have two vectors, if I give you two random vectors, if I say v is 3i minus 5j and w is 20i plus j, and if I ask you what is the angle between them, how would you do it? You would use both these formulae together. You would say that v dot w is v1 w1 plus v2 w2. So this is going to be 20 times 3 is 60, minus 5 plus 1 is minus 5. No? So this is 55. But also v dot w is magnitude of v, magnitude of w, and cosine of the angle between them. So basically 55 is, what is magnitude of this? 3 square plus 5 square is 25, 34 times, why did I take such huge numbers? 401 times cosine theta. So I'm not going to sit and do this, but from this you can find out what the angle between these two is. Yeah, any questions? So now we've already defined the dot product. Now we'll define the second one, which is the vector product or the cross product. So in the scalar product, we did vector times vector gives you scalar. Now in the vector product, we will do vector times vector gives you a vector. So if I have a vector v and a vector w, then V cross W, let's go to the next page. Oh wait, I should have discussed determinants first. Anyway, I'm going to assume you know what determinants are. Is there anyone who doesn't know what a determinant is? Please raise your hand. Okay, 3 people. Okay, I'm going to write down a notation for you. I'm going to tell you what it means, but I will explain it a little later what it really means. So I, J, K, V1, V2, V3, W1, W2, W3. So this kind of 3 by 3 thing is called a determinant. And I'll just introduce determinants right now. Never mind. Sorry for the little jumping around. So a determinant is essentially this kind of, well, not necessarily 3 cross 3. In general, it can be an n cross n grid. So if I say A, B, C, D, E, F, G, H, I, not I, because that is square root minus 1, J, let's say. So if I have this kind of grid, then the determinant of this is defined as follows. There is no temporary pen in there. Okay, never mind. So suppose, I wish I had a blackboard and you were in front of me, that would have been much easier. So I start with A, and then you cover the row and the column that A contains. Is that visible? Okay, good. And what you're left is with just is these 4, E, F, H, and J. And then you first multiply these 2 and then subtract from it these 2. So E, J minus F, H. Then you put a minus B. So now you're looking at this B element over here. Now you cover up the row and the column of B. And what is left is D, J, D, F, G, and J. So now you do these 2 minus these 2. And then the last one is C. So you cover up the row of C and the column of C. What you're left with is D, E, G, H. So again, you do these 2 minus these 2. So this is D, H minus E, G. Point is, you have to choose one of the rows or columns. We chose this one, which is the most common way of doing it. And then you take the first one, cover up its row and column, and do this to the 2 cross 2 part. And then you take the second element, cover up its row and column, and with the remaining 2 by 2 part, you define this. And then you take the third fellow, cover up its entire row and column, and then with what is left, you define this. And an important point is you keep flipping the sign. So the first term has a positive sign, second term has a negative sign, third term has a positive sign. So this is called a determinant, and it's very useful when you're trying to, for example, solve multiple equations in multiple variables. I will give you some practice, some links where you can find some practice problems to try these out. I'm guessing you have not understood what determinants are. Is that right? Do you have questions? Do you have too many questions?
No, it's clear. Thank you.
Okay, I'm not satisfied with what I've done, but if, well, okay, let's do a numerical example. Maybe that helps. We'll come back to this. So 1, 2, 3, minus 1, 2, 1, 0, 0, 2. So this determinant, to calculate this, I will say 1, and then I have this 2 by 2 block. So this is 4 minus 0. The second term is going to be 2. So I close this, and then I have, with what is left, I have minus 2 minus 0. And then in the third term, I take this one, so 3. So I close this, and I have 0 minus 0. And I make sure I change the signs and all of these. So plus, minus, plus. So this is 4, minus 2 is 4, 0. So this is 8. Okay, I'm a little happy this time. Is this slightly more clear what a determinant is? So we are going to do the same thing over here. This cross product is defined as this determinant. So this turns out to be I times V2W3 minus V3W2 minus J times V1W3 minus V3W1 plus K times V1W2 minus V2W. So as you can see, this is clearly a vector because it has I, J, and K components. So here is how you multiply two vectors together to make a third vector. One important thing to note is that if V cross W is some vector Z, then V and Z will always be perpendicular to each other, and W and Z will always be perpendicular to each other. So the cross product of two vectors is always perpendicular to those two vectors. Okay, let's take a short 3-minute break.